What if everything we know, everything we see, the entire universe, isn't just a random collection of particles and forces, but is actually running on a program? What if all of reality, from the tiniest quark to the biggest galaxy, is just following a single, elegant piece of code? Well, today we're going to look at a pretty bold new theory that claims to have found that very code.
All right, let's just jump right in. The central idea is almost deceptively simple. Forget the whole zoo of particles and extra dimensions we're used to hearing about. This theory says, let's start with just 6 fundamental things. 6 vibrating strings. But these aren't just any strings. They're vibrations. Their music is said to literally write the rules for everything else. So let's start at the very beginning, with the most basic building blocks of this whole new reality. I mean, how in the world do 6 simple strings create the 3-dimensional world that we all live in every single day?
Okay, so here's the first big idea you have to wrap your head around: emergent spacetime. The theory says that space isn't some pre-existing empty box that physics just happens in. Instead, space itself is an effect. It's generated by the vibrations of these 6 strings. So think about that. They're not vibrating in space. They're vibrating to create space.
So, how does that actually work? Well, the 6 strings form 3 pairs, and as you can see here, each pair is responsible for one of our spatial dimensions. But look at the ratios. This is the amazing part. They aren't random at all. They are the most stable, most perfect ratios in music. The x-axis is a 1-to-1 unison. The y-axis is a 3-to-2 perfect fifth, and the z-axis is a 2-to-1 octave. The proposition here is just incredible. Our 3D reality is literally built on a perfectly stable cosmic chord.
Okay, so if the strings are the hardware, you gotta ask, what's the software? Well, the theory proposes a single, powerful master equation that governs the whole show.
And here it is, the engine of the whole theory. This equation has this fascinating duality. It suggests that the curvature of spacetime, let's call it kappa, can be described in 2 totally equivalent ways, either as a function of information or as a function of geometry. They're like 2 sides of the same coin. It means you can look at the universe as a giant computer processing information or as a physical system of objects pulling on each other, and you'd be equally right both times.
Let's unpack this a little. On the left, you have the information term. This basically measures order versus chaos, or entropy. The theory makes a wild claim. A highly ordered system, like a complex crystal or even a DNA molecule, curves spacetime more than a chaotic gas does just because of its structure. It says information itself has weight. Now, on the right, you have the geometric term. This looks a bit more familiar. It's the pull from what the theory calls the information mass of everything else. But here's the kicker. The model says these 2 are just different ways of saying the same thing. An object follows a geometric curve through space because it's also trying to find a state of maximum informational order.
All right, so those are the rules of the game. What kind of universe do they actually build? This is where things get really wild, because all the familiar physics we know starts to just appear, not as fundamental laws, but as consequences of these simpler rules.
According to this theory, matter wasn't all created in one single Big Bang. No, it was more like a cosmological cascade, a series of steps. It starts with a source of primordial energy. This energy gets compressed by the active space-time field into these tiny high-frequency wave packets. And when these waves hit just the right resonant frequency, they kind of lock in and bam, you have the first stable quarks. From there, a simple set of attraction rules lets them bind into neutrons, which then decay into protons. And finally, those protons interact with space itself to form the first atoms of hydrogen. It's a creation story step by step.
And right here, this is probably the most radical claim of the entire theory. The electron, a cornerstone of the standard model of physics, it says it's not a fundamental particle at all. Instead, it's described as an emergent effect. It's a stable wave function that's created by a proton's charge interacting with this active vacuum. So think about what that means. The electron isn't a separate little thing orbiting a proton. It's what space itself does in the presence of a proton. Whoa!
And this idea of things just emerging from the system doesn't stop with particles. It extends to the physical laws themselves. Take the Pauli exclusion principle. That's the rule that keeps atoms from collapsing in on themselves. Well, in this model, it's not some complex axiom. It's just a simple rule. Particles with the same phase repel and opposite phases attract. That's it. It's like magnets. And even the quantum property of spin isn't fundamental. It's just a natural consequence of the 2-state, up-down nature of that emergent wave.
Okay,
Okay, this all sounds amazing, right? A beautiful story. But any theory can sound good on paper. The real question is, does it match reality? So let's look at the evidence from the computational simulations that were built to test this whole framework against the real world.
So this first test is really clever. It compares a standard simulation based on Heisenberg uncertainty with one using this theory's new principle. Now look at the energy drift. You see, most simulations kind of leak energy over time, they build up errors. The standard model here loses almost 1%, but the first quantum model, wow, it is incredibly stable. And the theory says this is because uncertainty isn't some fixed constant across the universe. It's a local property that actually goes down in areas with more information, more order. The system is literally self-correcting.
But that's just an internal test. How does the model do when you compare it to actual real-world data? Well, proponents tested its predictions against results from the Large Hadron Collider at CERN. And when they compared the predicted outcomes of high-energy particle collisions to what was actually measured, they reported a match of 99.8%. And this chart really shows you what that looks like in practice. It compares the model's prediction for how often really rare particles, like the top quark and the Higgs boson, should be created versus what CERN actually saw. I mean, look at those bars. The predicted numbers from the simulation and the real-world data are so close they're practically on top of each other, well within the margin of error. That's just uncanny.
And for the final test, the biggest test of all, cosmology. Could this model, starting from its very different origin story, reproduce the baby picture of our entire universe, the afterglow of creation? According to its authors, the answer is a resounding yes. Their simulations successfully recreated the exact pattern of fluctuations we see in the cosmic microwave background, a near-perfect match for the real data we got from the Planck satellite.
So, if this model really does hold up, if it proves to be a more accurate description of reality, what could that mean for us? Well, its creators claim it's not just a new description of reality. They say it's a blueprint for how to engineer it. And the potential applications that could fall out of this are just staggering. A potential solution to quantum computer instability using these special layered shields. A possible pathway to clean, limitless energy through low-temperature fusion. It even provides a design for a reactionless space drive that would work by pumping out a specific chord of frequencies to curve space-time in front of it. These aren't just theories, they're potential engineering blueprints derived right from the model's core principles.
And that leaves us with this one final, really profound question. This theory paints a picture of a universe that is fundamentally informational, a kind of cosmic computer running on these elegant harmonic rules. And if that's true, it suggests what the ultimate technological frontier might be, not just to understand the universe, but to maybe, just maybe, learn how to program it.